So the second section is very, very similar to the first section, except we have to look at the when we're comparing two means, how is it a little different than comparing two proportions? We'll cover how the shape, center, and spread of the sampling distribution of those differences is. We're going to look at conditions again, and confidence intervals and significance tests, and also making sure that we recognize that most of the time, you're going to be looking at a two-sample T procedure versus a paired T procedure. Just like in with the probability of the difference of two proportions, we're going to be looking at two different populations. Actually, use a highlighter. Two different populations. Right? And then from there, the things we're looking for, the population mean for the first thing and population mean for the second thing, we're going to call mu1 and mu sub 2, but we're mostly going to be dealing with the statistic of x bar and then the sample size of n1 and n2. So it's just exactly the same in this case as the proportion, except we're substituting the mu for our parameter and the x bar. To talk about how the sampling distribution of the difference between the two means is affected, what its center and spread and all that is, we're going to be looking at a situation that is not that common, where we actually know ahead of time what the standard deviation and the means of each of the populations is. So remember, we normally, we're looking for information about the population parameters of mu1 and mu2, and we need to use a standard deviation of that population, but very rarely do we actually have those things. But in this situation, we're looking at that. And I want to remind you how we can write. Whoa, that's fun. I don't know, that was fun. Or how we can write that information. Here we have the heights of 10-year-old girls and 10-year-old boys, a national average. And remember, we can write, oh, that's interesting. It's not letting me. Whatever. I'm just going to show it to you here. Remember, when we put the n in front of it, that means that the population is normal, whatever population we're talking about. And then the first number is your mean, the second number is your standard deviation. So girls, it's a normal distribution of 56.4 and a standard deviation of 2.7. And for boys, it's 55.7 and 3.8. We're going to compare this, this known mu1 and mu2 and the standard deviation, the known standard deviation 2.7 and 3.8 against an SRS of 12 girls and 8 boys. So we can look at the difference between sampling distributions of known parameters and the statistics, etc. So the SRS of the 12 girls here is what is going on. We have the mean is 56.4 and the standard deviation is 0.8. And the shape's approximately normal. And here are boys. The standard deviation is 1.35, and the mean is 55.73. When we put them together, these are random variables, we're taking the difference of them. The mean is going to be the difference of the means of XF and XM, and the shape is going to be approximately normal. And we're going to check on those conditions later, but since the original population was approximately normal, both of them, then the distribution is going to be approximately normal. The spread, on the other hand, is where we need to pay attention. It's not going to be the difference of the standard deviations or the sum of the standard deviations. It's going to be the sum of the variances. And we'll talk about what that's going to look like when we only have samples in a moment. There is a summary in the textbook about this in words, but I like this visual much better. When we're looking at the sampling distribution of x bar 1 minus x bar 2, we're going to find that the mean is going to be right there at x of the population, mean minus the population the two population means. However, we rarely have those, but that's one of the definitions of a non-biased biased measure, is that the sample will equal the population, the sampling distribution mean. So we can find the mean of the sample of the difference by subtracting them. And then the standard deviation is always going to be, when we combine two random variables, whether we're subtracting them or adding them, it's going to be the sum of the variances. And then we also, of course, have to have our standard error components, which is this dividing by n. We rarely are going to have this population standard deviations, so we're going to use the sampling standard deviation instead. And so the sampling standard deviation squared divided by n1 plus the sampling standard deviation squared of the second sample divided by n2 will be how we find our margin of error. So when we're combining two means, finding the difference of them, we can either be interested in running a confidence interval or a t-test. And remember, we're going to be using t-statistics and t-tests because we very, very, very rarely have our population standard deviation, which would allow us to use a z. The minute you start using your sample for standard deviation, that's when the t distributions occur. So, but the same conditions need to be met. It needs to be random at 10%. Then we can go ahead and use the standard deviation formula. If the 10% condition, if it's over 10% of the population, remember that no longer are we talking about independence. Sometimes when we're doing experiments, by the way, we don't have to check the 10% condition. We'll talk a little bit more of that in a second. And then if the normal condition is met, we can go ahead and standardize with a t-statistic. So remember, our t-statistic is going to be, the t-statistic, it looks just like, the formula for a t-statistic is exactly the formula for a z. So you're always going to be talking about the data point and minus the mean all over the standard deviation. And that's the basics. We just need to remember what is our data in this case, what is our statistic in this case, what is our mean, and what's our standard deviation. So here, we don't know the parameters of the standard deviation sub 1 and standard deviation sub 2. So we know we're going to have to use the sample, and we're adding the variances, which is why they're squared. So the standard area always goes in the bottom part of our z or our t. In this case, the t-statistic, the data piece comes from the difference of the x-bars, and then the this is the population. But for most of the time, for when we're looking at difference of means, we're assuming that the difference will be 0. So almost always this number is 0. And then since we're doing a t-statistic, remember we're going to be dealing with a t-distribution. And either we can use the smallest of the two differences for degrees of freedom, or the calculator will do it for you, and we'll know how to read that in class. So the conditions are the conditions. They have to be met for both samples. That's the key issue. And remember, you are checking the random and 10% to make sure that they are independent. If it's more than 10% of the population, you cannot use the standard deviation formula because they're no longer considered independent. It has to work for both. And then the north and normal or large sample, remember the key things you're checking for. And if the original populations are normal, you're done. If they're greater than 30, each of them, you're done. If neither of those are met and it's less than 30 and you don't know anything about the original population, then you need to graph each one and make sure that there's not a lot of skewness or outliers. And it's only then can you use t-distributions. When doing the confidence interval, it's the same basic thing where you're talking about the statistic, critical value, and the standard deviation. So for the difference between two means, your statistic is going to be the difference of the x-bars. Your t is going to be based on the degrees of freedom, which either you're going to take the lower of n1 minus 1 or n2 minus 1 if you're going to use the table, but I highly recommend you use technology if you run your confidence interval using a two-sample t-interval. It's going to give you a much better degrees of freedom, and it'll tell you the degrees of freedom, which you can then indicate in your writing. And then remember that the standard deviation is going to be the sum of the variances of the two samples, and then of course the error part is the n1 and n2, the division there. Same conditions need to be met for any inference, whether you're doing a confidence interval or a significance test. But remember, when you write a SIG test, we're going to have to write a null and alternative hypothesis. The null hypothesis in this case is looking at the difference between the two populations' means, and very often this hypothesized value, if there's not an accepted difference between them, it's going to be that there is no difference and that it's 0. Alternatively, we can write the null hypothesis. If the difference is 0, then that means that we're assuming that the two things are the same. That kind of writing, actually, I find easier than the alternative hypothesis being written like this. So this one says the difference of the two is going to be greater than 0. You can also write that same thing as one is greater than the other, and et cetera, et cetera, et cetera. Or one is U1 is less than U2 or not equal to. And that sometimes is easier to figure out what you're going to put in the calculator in terms of greater than or less than. So write it that way, but that's up to you. So to run a significance test, you got to check your conditions, make sure it's true for both samples. Then for your null hypothesis, once again, this part is the difference of your sample means, and then this part is almost always going to be 0 unless it's indicated in the problem what the accepted difference between those two is. And then your standard error, remember, is the sum of the variances divided by n1 and n2. That didn't sound right. The variance of 1 divided by n1 plus the variance of 2 squared divided by n2, and then the square root of that, so the sum of the variances. And then you're going to find the p-value. You are either going to use the smaller of those or use technology. And remember, when it's greater than, it's a one tail. When it's less than, it's a one tail in the other direction. And when it is not equal to or different from, you're going to be taking one of the tails and doubling it. When you're using T procedures, for reasons that we're not going to go into too much, when you're planning a two-sample study, the best is to have equal sample sizes. We do not pool sample T procedures, two-sample T procedures. It asks for it in the calculator, but we just don't do it. It's just not how we're dealing with it. When you compare two means in a randomized experiment, you're safe using T procedures, but we don't when we have paired data. Remember, paired data, you're looking the difference of each of the individuals in the pair, what you're doing analysis on, so it's really only one sample, as opposed to two-sample T procedures are two different populations. Paired data is one person or one thing done two different ways, and so that's a one sample. And always remember that if you have not randomized from the population, a larger population of interest, you cannot make generalizations to that population. You can only make generalizations that are of people that are similar to the ones in the survey or experiment. There you go. Remember. Shape, center, spread has to do with the variances. The sum of the variances, that's a common place that people get confused. You know what your conditions are, but make sure that they are true for both samples. And little picky thing, degrees of freedom, you're going to choose the smaller of the n1 minus 1 or n2 minus 1 unless you use the calculator.